Welcome friends, let us today learn an analytical technique to determine the stability of a linear time invariant system. Yes, this technique is none other than the Routh Stability Criterion. So the points we are going to consider in this session are: see the characteristic equation of an LTI system, study the Routh Array, study the Routh Stability Criterion and understand it and apply it to solve various problems for determining the stability of LTI systems using the Routh Stability Criterion. So let us start. As we should know that the stability criterion study of linear time invariant system has been developed for centuries, I should say, and the Routh Stability Criterion is one of the well accepted and known technique. This is as well a technique which will give you a sure shot question or problem in the examination. So from that perspective also this is very important, because a problem on Routh Stability Criteria is always solved by the learners easily. Before we go for the Routh Stability Criteria, we should know that the criteria was first proposed by the Hurwitz, named as the Hurwitz Stability Criteria. The Hurwitz Stability Criterion. So in the Hurwitz Stability Criterion, we obtain a Hurwitz array. Using that array, we obtain a matrix, and for certain parameters of the matrix we check whether the values are changing its sign or not. A little more convenient technique to determine the values of certain parameters of system variables, which are the coefficients of its characteristic equation we are going to learn. We determine whether the system is stable or not. So we'll study the Routh Stability Criteria, based on which we can solve the problems on LTI systems. So let me write it: the Routh Stability Criterion. The Routh Stability Criterion. So the Routh Stability Criterion is an analytical procedure for determining if all the roots of the polynomial have negative real parts, and it is used in the stability analysis of linear time invariant system. So if there are certain delays in the systems, for that we have to make certain changes so that the delay, or that is the dead time, can be approximated to convert it into a system in which we can get a characteristic equation or the polynomial equation. So we shall start with determining the polynomial for a given LTI system. So let me give the heading: the characteristic equation. So the characteristic equation is obtained for LTI system. Let us write the block diagram for a LTI system. Say this is your GS, the Laplace transform of the plant, and this is getting some control input as the output of a controller, KS, and output of GS is the plant output YS, and this is measured and sent to a filter HS for comparison with the reference input. So we have the reference input over here. The reference input in Laplace is RS. Then we have a feedback signal. So this is plus, here this is minus. So from this I can write the equation YS equals to GS KS. The error signal will be here at this point, so it is multiplied by the error signal. Again ES, the error signal is obtained as the difference between the reference input and the feedback signal, which is here HS into YS. So if we place the value of ES over here, we can say that YS equal to GS into KS multiplied by RS minus HS YS. So this means that you have YS equal to GS KS RS minus GS KS HS YS. So if we take the Y terms together, so we can find out that 1 plus GS KS HS square bracket, I am assuming the system to be SISO type, system to be of SISO type, so this will become single equation finally, so equals to GS KS RS. So if we divide both sides by the factor on the left hand side, we will get YS equal to GS KS divided by square bracket 1 plus GS KS HS. So this is multiplied by RS. So from here we can get the transfer function TS equal to YS by RS equal to GS KS divided by 1 plus GS KS HS. Now we see that the denominator on the right hand side has got a special form, and for any value of s for which this denominator becomes 0, that value of s will definitely determine a factor or root of the system. So we can assign QS as a polynomial equal to 1 plus GS KS HS, which is the denominator, and this is the characteristic equation given as QS equal to 0. It means we have to find out all the roots of this value or this polynomial so that the RHS should become 0. So the characteristic equation of any linear time invariant system can be represented by this, and we can generalize this characteristic equation QS as A0 s power n for nth order system plus A1 s power n minus 1 plus A2 s power n minus 2, like that up to an minus 1s plus an equal to 0. So this is the characteristic equation of a system generalized to the nth order system. Once I get the characteristic equation, I can obtain the Routh array from this equation and go for analytical treatment through Routh stability criteria. So let us write some important points about Routh stability criteria. The Routh stability criterion what are those points? As I have already mentioned in the beginning of a discussion, that number 1, the Routh stability criterion is an analytical procedure, is an analytical procedure for determining if all the roots of the polynomial, if all the roots of the polynomial here it is QS, have negative real parts and is used in the stability analysis of LTI systems. Stability analysis of the LTI, that is linear time invariant systems. Linear time invariant systems. Second point, so the second point I should like to mention is that it is based on ordering of the coefficients, of a characteristic equation which is Q is equal to 0 over here into an array which is defined as the Routh array, that gives the necessary and sufficient condition for stability of a linear time invariant LTI in short. So linear time invariant system model. So once we got the characteristic equation, from this we can form an array and based on the coefficients of the array we can determine whether the system is stable or not. So this is both the necessary as well as the sufficient condition, because once you establish that the system is not stable, it means system is unstable, right? So this is the plus point about this criteria, that it directly gives you the idea of a system whether it is stable or not stable. So let us form the Routh array. So we form the Routh array. How we can form it? Because we got the characteristic equation as qs equal to a0 s power n plus a1 s power n minus 1 plus a2 s power n minus 2 up to an minus 1 s plus an equal to 0. So for this I have to form array like this. We start from s power n, we'll start reducing to the power of s. So s power n minus 1, then s power n minus 2. In this way we will go to a column in which it finishes at s power 0. Now the coefficients a0, I write a0 first, then next I write a1, then I go to the second column, we write a2. So here I should write a2, then a3. Next I will write a4 over here for s power n, then a5 for s power n minus 1, like that I can proceed. Here on the below of a1 I find some new coefficients, that is b1, like b2 and so on. Similarly for next line I get c1, c2 and so on. So by the end, if you do it, you will see that the last term should be an. So once I form the array, I should be able to determine the values of the coefficients like b1, b2, c1, c2, like that. So here first I determine the coefficient b1. You go for the determinant from here. So this is the matrix. What is the matrix? We have a0, a1, a2, a3 as the matrix. So I get the determinant of this matrix, put a negative sign and divide it by a1. Similarly for b2 I get the first column and the third column like this. So this should give me minus determinant of a0, a1, then a4, a5, like that. This should be divided by again by a1. So similarly we can find the other coefficients. So you can find the coefficient c1 equals to minus determinant of, you go to the second and third row over here, so you can get this determinant and this determinant. So we can have determinant of a1, b1, then a3, b2, like this. This should be divided by b1. Similarly for c2 I can have minus determinant of the matrix, which is the first column and the third column. So this is a1, b1, then a5, and b3. This is b3. This divided by b1. So likewise we can obtain all the coefficients starting from b1 to an. So with little more simplification I get b1 equal to a1 a2 minus a0 a3 divided by a1. Similarly, b2 equals to a1 a4 minus a0 a4 divided by a1. Similarly, c1 is b1 a3 minus a1 b2 divided by b1, and c2 equals to b1 a5 minus a1 b3 divided by b1. So likewise all the coefficients or the elements of the array for Routh array can be obtained from where the sign of the first column will be important for us. So we see that the sign of the first column, this column will give us the stability analysis for the system. So we study the sign changes over here. So when we are making the characteristic equation and further we go up to the Routh array, we have certain considerations. So what are those considerations? What are those considerations? Considerations in making of Routh array. What are those considerations? Consideration number 1, the missing coefficients may be taken as 0. The missing coefficients of characteristic equation QS equal to 0 may be taken as 0. However, there are exceptional cases to be considered. However, there are exceptional cases to be considered. That we shall learn what are those exceptional cases. If a0 is greater than 0, then all the coefficients of the characteristic equation, that is QS equal to 0, should be positive. Right? So in that case, if we see that the characteristic equation has coefficient of a0 as minus or negative, so all the coefficients starting from a0, a1, a2 up to a, they should be negative, like that. They should be of the same sign. Next, point 4. If this is in the Routh array, in the Routh array. If a0 is greater than 0, then all the terms in the first column, then all the terms in the first column must be greater than 0. That is, I have a1 greater than 0, b1 greater than 0, c1 greater than 0, up to an greater than 0, like that, for stability test conformity means to satisfy the stability test, all the terms of the first column should be 0 if first element a0 is greater than 0, and if not, then the system is unstable. If not, then the system is unstable. So in that case, the number of sign changes in the first column is same as the number of roots of the characteristic equation on the right half of the S-plane. So let me write in words. Then the number of sign changes, the number of sign changes in the first column, is same as the number of roots of the characteristic equation, that is q is equal to 0, on the right half of the S-plane. So this is how we determine the stability of a system. So let us try an example so that we can understand that how simple the technique is. So let us take a problem. Test the system. Test the LTI system s power 4 plus 8s cube plus 18s square plus 16s plus 5 equal to 0. So we should draw the Routh array first. So it should be written in the question as for Routh stability criterion, or Routh stability criterion. So for that, let us draw the Routh array first, because we have seen that no coefficients are missing, all the coefficients are of the same sign, so we can readily go for the Routh array. So let us draw the Routh array like this. We are starting from s power 4, then s power 3, then s square, then s power 1, s power 0. So first element coefficient is 1, then 8, then go to the second column 18, second column second element 16, then go to the third column 5. Now we have b1, b2, and if here we don't have an element, we can consider it as 0. So b1, b2, then c1, c2, then this should be definitely an 5. So let us obtain one by one. b1 equals to, so we had find out that the coefficients value a1 will be multiplied by a2, so a1 multiplied by a2 minus a0 multiplied by a3 divided by a1 will give the value of b1. So this is 8 into 18, 8 into 18 minus 1 into 16 divided by a1 is 8. So this value can be solved to 16. Similarly, b2 can be obtained as 8 into 5, because this is a1 a4 minus a0 a5 divided by a1. So this should give you 8 into 5 minus 1 into 0 divided by 8. So this should give you the value of 5. Similarly, c1 can be obtained as the negative determinant of a1. This is a1, b1, then this is a3, then b2, so divided by b1. So this becomes b1 a3 minus a1 b2 divided by b1. So this is equal to b1 is 16 over here, so we write 16 into a3. So you have a3 again. From here you see the array 16, so this is 16 to 16 minus a1 is 8, so you have 8 into b2, so b2 is 5 over here, so we write 5 divided by b1, which is again 16. So from here c1 becomes equal to 13.5. I have calculated it beforehand, so I am writing the value directly. You can calculate it yourself and check whether it is right or wrong. Then c2, so for c2 you have the coefficients like this multiplied by this and this multiplied by this, so this directly becomes 0. So because c2 becomes 0, so when I go to the last element, this is your c1 multiplied by b2, so c1 multiplied by b2, your b2 is 5, then c1 is your 13.5 minus b1 divided by b1 into c2 divided by c1, so c2 is 0, so we are left with the last element d1, we are left with c1 b2 divided by c1 equals to b2, so that automatically becomes 5. So that is how the last element becomes 5. In this way we can find the elements of the Routh array, and from that estimation we obtain that b1 equal to 16 is greater than 0, then This is the first element, that is the third element in the first column, that is greater than 0. Fourth element in the first column, C1. So C1 equals to 13.5 is again greater than 0, and that is D1 equals to 5. This is again greater than 0. So ultimately we find that entire column, that is the first column in the Routh array, is greater than 0. This is the first column in the Routh array is greater than 0. That is why the system is stable. So the system is stable by Routh stability criterion. Similarly, we can find out the stability test and stability of different kind of systems through its characteristic equation. Let me give you another problem on Routh stability criteria. Problem. Test the system with characteristic equation 3 s power 4 plus 10 s cube plus 5 square plus 5s plus 2 equal to 0 for Routh stability test. So students, take it as homework, and once you finish watching this lecture, please try it yourself, and tomorrow we shall work it out to check for the correct answer, and we shall find out some other typical examples of system and its characteristic equations, which are the special cases we require to know such special cases for solving the problems on Routh stability criterion. So this much is for today. So the concept discussed in today's class has been majorly taken from the book by Professor M. Gopal on control systems. You can refer to it as well. So students, if you find this video useful for you, please like it, and if you have not subscribed the channel so far, please subscribe it so that for the next video you can get the upload directly, and also you can have the playlist to refer to the previous lectures easily. So for subscribing, you have to set the bell icon for getting the notification, and you can always ask me question through my email ID controlsystemsfaq@gmail.com. Thank you for your patient listening.